Good morning, students. So, we are going to learn on continuation of basics measurements, electrical and electrons measurement, third semester, C18 students. In that, we are going to covering the basics of measuring instruments. Now, up to this class, we have learned basic things. What is the definition of terms used in our electrical measuring instruments like measurement, accuracy, precision, tolerance, resolution, sensitivity, error, some definitions. After that, we have seen that the classification of instruments, whether it's analog instruments and digital instruments. Analog instruments will read the continuous physical quantity, whereas digital instruments will read intermittently values, whether 0 or 1 value. And at the same time, we have seen that different type of the classification based on the different with the instruments, absolute instruments and second instruments. In second instruments also we have seen further classified indicating instruments, recording instruments and integrating instruments. Indicating instruments is nothing but the value directly will given to the value to be measured on a calibrated scale. Indicates the value at that instant. For example, a meter that will shows the current flowing in a closed circuit at that instant on a calibrated scale. Whereas a recording instrument, the recording instrument which records the value on a paper. Permanent recording is taking place based on time passes. A good example is the seismograph. At the same time, ECG. ECG is taken for the heart patients generally. So, it will take the heart beating on a graph pulses for a specified period. And whereas the integrating instrument is the combination of two. That means it integrates the value from one period to the required period. They combined all values. A good example is the energy meter, generally used in our domestic applications. Energy meter continuously record the how many units consuming for every day up to till 1 month. Based on this cumulative value, so NPDCL people will charge the tariff values. Some current bill will give us. Okay, that is the different type of the instruments, absolute instruments and the second instruments. At the same time, we also covered absolute instruments are the very precision type of instruments and is accurate instruments that will gives the value in terms of its deflection and with the meter constant. Whereas the secondary instruments will gives the values only directly on the deflection value, no need of the meter constant. And after that we have covered that. So, this is what are the different type of the energies required to operate these instruments. That is the magnetic effect, magnetic force is required, and electromagnetic, electrostatic, electrodynamic and hot wire, different type of the energies is required to shows the values to be measured in a instrument. Any physical quantity converted into our electrical value. That purpose we require these are the different type of the energy forces is a magnetic effect, electromagnetic induction effect, electrodynamic effect, thermal effect, chemical effect, electrostatic effect and Hall effects. These are the different type of the effects, nothing but energy is required to operate our instruments. And after that we have seen that, so what are the different, the torques is required to show the required values. So in that one we have seen that the basic torques is a deflecting torque, controlling torque and damping torque. So in deflecting torque we have seen that, what is a deflecting torque? So what are these energy forces, effects, this electrostatic, electrodynamic or hot, this all affect all energy sources based on these physical quantities, our deflection changes. So that means here the whatever the input value is given, that is converted into the deflecting force to deflect the pointer from 0 position to the final position on a calibrated scale. That is a deflecting torque. The torque is generated, produced with the help of the input physical quantity. So it always moves in a clockwise direction as a from 0 position to the final position. And coming to the controlling torque, once the pointer, due to the deflecting torque, the pointer is moving from the 0 to, for example, at 110 degrees from left. After that there is no deflecting torque is removed, disconnected, then no deflecting torque, but due to the gravity the pointer will try to move towards the right side. So instead of coming to the left side, it will goes to the right side due to the gravity bottom. Suppose I want to measure the another reading, so I have to bring this pointer to the 0 position manually. So that is a unnecessary discernment. So what to do? If deflecting torque is produced, if there is no deflecting torque, the pointer has to come to 0 position, and that means it is ready to measure the next value. But how it is possible? So at that condition we require this controlling torque. The controlling torque will oppose the deflecting torque always. Whenever the deflecting torque equal to the controlling torque, the pointer is stable at that point, that is the required final position. So the deflecting torque equal to the controlling torque. Initially the deflecting torque at 0 position, the controlling torque is dominating. Once the deflecting torque is go on increasing, the controlling torque is go on the charging its force. Once it is moving at one position, this controlling torque opposes the deflecting torque. Both torques are equal. At that condition the pointer is stable. So at that stable pointer we are taking the reading. Once deflecting torque equal 0, then controlling torque try to move the pointer towards its initial position, that is a 0 position. That purpose already you have seen. So deflecting the controlling torque can be produced by using the spring control mechanism and is a gravity control mechanism we have seen previously. The phosphorus branch hair springs are used in both sides on a spindle to work as a controlling torque, or sometimes we can use some weights are used as a gravity control. And even if you are using this controlling torque and it opposes the deflecting torque, the pointer will reach to the final position, and at that condition there is a oscillation takes place before coming to the stable. So what happened? So due to the input supply, the more deflecting torque, but controlling torque is limited. Then due to this one, what will happen? The deflecting torque is try to move the pointer away. Then but the controlling torque at that angle it pressed or stressed and try to move the deflecting torque opposite direction. deflecting torque move the other direction, controlling torque move this direction. So go on this changing its resultant values, the pointer is subjected to oscillation at final position before coming to the 0 position. These oscillations are known as should be damped, should be nullified. So because I want to take the reading very quickly, I cannot wait for the few seconds, so still the pointer has stable position. So these oscillations can be reduced, overshoot, undershoot can be reduced by using another force, another torque, that is known as a damping torque. So this damping torque can produce the different methods. So already we have seen the under damped, over damped and critical damped. So last class. So under damped means the oscillations taking place. And so here over damped means it will go so very slow. And critical damped is going in a parabolic position. We have seen last class. Now let us see how we are going to produce a normal damped, that is a critical damped, and how we are going to produce the damped to avoid the oscillations at the final position. What are the methods? Physical methods are used in our instruments. Now let us see that one. So these are all we have seen already. Okay, let us enter our subject. This overdamped already we have seen. Now on completion of this period, you would be able to know that the type of damping, that is the air friction damping, fluid friction damping and eddy current damping. These three dampings are generally employed in our electrical instruments to nullify the oscillations. Okay, so how this air friction damping works? What are the internal parts of damping? How this air friction damping connected to our instrument, whether it is a voltmeter, or ammeter, or wattmeter, or energy meter. Let us see one by one in details. Now classification of damping torques. The damping torques are classified based on the media used to damp the oscillations. Here I used the air as a damping media, air friction damping. Now here instead of using the air, I can use a liquid, then we can say this is the fluid friction damping. And I can use our electrical energy, that is another force is the eddy current damping. So here the damping torque can be produced by air friction damping, fluid friction damping and eddy current damping. Let us see how we are going to nullify the oscillations with the help of these medias. Okay, let us go. Now air friction damping. Air is used as a medium to suppress the oscillations in an instrument as shown in the figure. So here you can observe at a glance, you can see just like air friction damping, there is a, you can just like it is nothing but some injection syringe. If you remove the needle and there is a cylinder and piston inside, so same operation takes place here also. Sometimes you can observe cycle pump also, air pump. For the cycle tubes, we are using the cycle air pump, similar method. So here what is happened, figure just at a glance you can see it, there is a air chamber, in that one there is a piston. So the piston will move in air chamber forward and reverse, so that is coupled to our spindle. Now the spindle is moved connected to our pointer. Once the spindle is moved by the deflecting torque and the pointer will move towards clockwise direction, then what is happened? The piston which is inside the air chamber try to move towards the down. But what is happening? In piston, before the piston head, there is a suction is created. The suction does not allow to move the piston towards the down. That means there is a force is applied. It is a try to pull the piston towards the suction. At that condition, the spindle subjected to oppose the some force here. So it is opposing the deflecting torque similar to the controlling torque. Now single person deflecting torque. Now opposite two leaders, one is the controlling torque, another is a damping torque. Whenever the deflecting torque is equal to sum of the controlling torque and deflecting torque, then the pointer will stable. Now, so damping torque is provided, then due to the quarreling between deflecting torque and controlling torque, there is a subjected to oscillations. So this due to the oscillations, the pointer will oscillate. Once the pointer is easily oscillates, due to this, if connected to the damping torque, the piston which is in the air chamber doesn't allow to oscillate at final position, because there is a suction is created. The suction doesn't allow the piston move freely, so thereby the oscillations nullified at a final position. Okay, this is a basic idea. Now we can see the physical, the air friction damping used in our instruments. Here you can see here. So this is a aluminum air chamber. Inside there is a piston. Here is the piston head, and it is connected to our spindle. So these are the gravity control. You can know the gravity controlling torque. This is a spindle. Now what happened? So here is a closed one. It is moving. This pin is try to move towards this direction. Once moving this direction, the pointer will try to move this direction. But if it is moving this direction, it has to come this direction. Once the piston is moving this direction, there is a suction created here. The suction doesn't allow the piston to move this direction. Some opposition force is developed here. Due to that force, the pointer may not overshoot the final position. Okay, let us see one by one. Now air friction damping. So you can see the parts of the air friction damping. So this is a scale, calibrated scale. The piston head is the nothing but this one. Now there is a cylinder. This is the piston. Now you can see this is the piston. This is the piston head. This is the cylinder, closed cylinder. Okay. Now piston. Next, this is the air chamber. Air chamber is a closed one. Next, this is a spindle. These are the parts of a air friction damping arrangement. Now here you can observe this is a black color. This is what is the suction is created. The suction try to attract towards this direction. Now the compressed air, that's the air is inside is compressed when moving the piston head presses towards this one, because the air there is no chances to escape. So this air is opposes the piston moving towards the left side. Okay. Now say here you can see the figure. So a light aluminum piston is moving in the air chamber. So this one arrangement is connected here. So here this is our air friction damping. Inside there is a piston. The piston is simply the light aluminum piston, lightweight. The clearance between the piston and the sides of the chamber should be less and uniform. So here, so this is a cylinder, this is the piston, and it should be, this is a gap here in the center, these places should be perfect. Otherwise what will happen? Whatever the suction may not be created here. So here this should be uniform, the piston head, and this should be uniform. Now, so you can see it how the oscillations is taking place on a scale. During the oscillations, the piston is trying to move in a in the chamber. So here the air compresses one direction, suction is created another direction. So it is nothing but opposes the deflection torque. So once the moving, the suction is created, and once moving in this direction, compression of air takes place. This either direction there is a force is developed. This force is in addition to the controlling torque, then the pointer will stop at that final position. Okay, this is a mechanism. You can see the analysis. Now, when the piston moves inside the chamber, pressure is developed in the chamber. The pressure inside the chamber opposes the motion of piston. When the piston moves away from the piston head, vacuum is created. That means here you can observe one thing. So here is the piston cylinder. Now this is a closed one. Now it is also closed one. Now I taken the another this one, and here is the one piston rod. It taken, this is the outside. Okay. Now what is happening? Once suppose this is moving this direction, here is the air presence. Air is compresses if moves this direction. If it moves this direction, here the suction is created. The suction doesn't allow towards this direction. The air compression doesn't allow this direction. That means the piston head subjected to two forces, either this direction and either this direction, due to the arrangements. That means now it is connected to our pointer. What is happening? So now this is connected. This is connected to our pointer here. Now what is happening? If deflecting torque is applied here, it tried to move this direction. But what is happening? Here suction, it doesn't allow move this direction. If deflecting torque is more, then easily overcome this period and it will move this direction. Some opposition takes place. Due to this opposition, the pointer doesn't overshoot the at final position. Suppose I want to show this is the value. So if there is no damping torque, it will go this direction first initially, and due to the controlling torque, it will come this direction. After that, it will go this direction. After that, it will come this direction. After that, it will show the final position. But due to presence of this damping torque, so due to the deflecting torque and due to the controlling torque, so it doesn't overshoot and undershoot continuously. That is, oscillation may not be possible due to the suction, due to the air compressor in the cylinder. So due to this one, so we are going to nullify the oscillations at the final position. This is known as the air friction damping. The vacuum inside the chamber opposes the motion of the piston, and which in turn arrests the oscillation of the pointer. Air friction damping precautions. What are the precautions to be taken while using this type of the damping in our instrument? The piston should not touch the walls of the chambers. That is, if the touches, what will happen? Friction takes another opposition force. So it should be slide on the chambers walls. Okay, this is one example. The precautions to be taken while preparing this one, where we are going to use this type of the air friction damping in our real life. So this can be used in hardware instruments. That means temperature measurement instruments. We are going to use this type of the damping instruments. When temperature changes, the pointer will changes its position. To avoid the overshoot, undershoot of the pointer on a calibrated scale, we are going to use this our air friction damping, and it can be used in MI instruments, moving iron instruments. What do you mean by the moving iron instruments? We will see later. And we can see this type of the instrument also in the dynamometer type instruments. So this is the moving coil instruments, moving iron instruments, dynamometer type instruments are the different type of the instruments generally used in our electrical engineering measurements. So what are those are we will see later. Okay. So generally dynamometer type of instruments are wattmeters. The wattmeters, in wattmeters we are going to use this air friction damping. These are the some application of dampings. Now coming to the air friction damping. So instead of air, now I am going to use some fluid or some liquid. Some viscosity liquid is used to oppose the flow of easy flow of veins or disc. So if the disc is moving in air easily, but same disc is moved in a liquid, somewhat opposition forces takes place. This type of the technique we are used in our instruments. Okay. So you can say how we are going to use that, you can see it. The fluid high viscosity damping oil is used as a medium to suppress the oscillations in an instrument as shown in the figure is known as the fluid friction damping. Now you can see the practical example of damping instruments. One instrument here, this is a one chamber, you can observe here. Okay, color you can change it. Now you can see, so here you can observe this thing. So this is a one example of the thing. So there is a fluid friction damping. Here this is a vein, so it is a shape just like you can see it. So connected this one, this is the fluid friction damping. There is a fluid, there is a spindle, it is connected to the one pointer here. This is a pointer on calibrated scale. Then what is happening? So once it's moving, it will try to move this direction, or you can is moving this direction, this direction, and this direction. So once what happened, under there is no liquid, so once it's moving, it is also moving very freely. But so instead of this one, I am filling with another material, that is a high viscosity liquid. Then automatically this liquid, what will happen? So there is no path to escape. So what will happen? Automatically it avoid the movement of this vein easily. So thereby it is connected to our pointer. As the pointer does not move freely, and overshoot and undershoot takes place at final position. This is the concept. Okay, let us see one by one. Now fluid friction damping. Here you can see it. It is a spindle, and this rotation takes place while it on, and veins, here you can see the vein. So rotation takes place, and this due to the rotation, so what will happen? So this is the vein, this is a vein, this is a vein, this is a vein. So in liquid it experiences some opposite force. It cannot easily move this one. So once it's moving, so what will happen? There is a opposition takes place in a liquid. So that opposition is required. Now disc and oil, this is the same oil. By seeing the plan, we are going to this one, we are seeing this here elevation. Now the veins or discs are attached to the spindle of the moving system. It dips into the part of the damping oil. The friction of the damping oil opposes the motion of the moving system. The damping force increases with increase in a velocity of veins and velocity of the oil. That means if the movement is more, automatically opposition also more. And for example, it can be used the Kelvin electrostatic voltmeter. I think you understood this thing. Now the fluid friction damping, the properties of the damping, which type of the oil you are going to use inside oil liquid. Now the good insulating oil and non-evaporating, it should not be evaporate, and it not corrosive oil. So this property is required at the same time, and the important is the viscosity should not change with the temperature. So based on the temperature, viscosity changes, automatically the opposition force changes. Due to this one, the value which is going to show on a calibrated scale also changes. So these all properties required for a liquid. This liquid should be constant and that should be work perfectly. So this is the air friction damping. That's a liquid friction damping. Now what are the disadvantages? Due to the liquid, it may be there is a possible to leakage. That is the one main disadvantages. So oil creeps out if the sealing is not perfect. The sealing is not perfect, oil may not oil comes out from the chamber. The instrument should be in vertical position only while doing this one. So the it should be kept at a vertical only. If you place it in the horizontal, the reading may not be accurate. So that is the fluid friction dampings. Now coming to our electrical damping is eddy current damping. So what do you mean the eddy current in damping? So eddy current induced in a conductive metal disc is used as a medium to suppress the oscillations in an instrument as shown in the figure. So what is the figure? Here you can see. So let us here understood the carefully, you can listen here. So what is happening? So this is a spindle and here is a disc, aluminum disc. One spindle is rotated, disc also rotating freely. Okay. Now what happened? So here now in the second case, I placed the one magnet at north pole and south pole here. So once north pole, south pole here, there is a magnetic lines of forces between the north pole and south pole. And this aluminum disc is moving in our this magnetic field. Once it's moving in a magnetic field by motion, then as per Faraday's laws of electromagnetic induction, it induces a EMF in the disc. Now the disc is cutting the lines of forces. As per Faraday's laws of electromagnetic induction, whenever the conductor is cutting the magnetic field, it induces a EMF in the conductor. Then automatically a EMF induced in the aluminum disc. This aluminum disc is a continuous one and is a closed path. Once it is a closed circuit, there is a current is passing through this one. Once the current passes, there is a own magnetic field developed in the disc. And this magnetic field in such a way that it always opposes the cause of its production as per the Lenz law. Lenz law. So as per Lenz law, it cause of its production. What is the reason to produce this flux? It is due to the rotation, due to the motion. So if the flux produced in such a way that it opposes the flow of the production of cause of it. So it is produced due to the rotation of disc. So if the disc is linked, there is no rotation, there is no EMF induced because static. Once it's rotating, it cuts the magnetic field, then it induces the EMF. Due to the EMF, current is flowing. Due to the current, it is a flux is induced. This flux is always oppose the cause of its rotation. So automatically the speed of the spindle, now before producing this flux, suppose RPM is 100 RPM. Now due to this one, the field is opposite the rotation, then the speed may not be 100 RPM, it may be 95 RPM. 5 RPM is reduced due to the opposition of the magnetic field. That means the speed changes now. So students, you can observe this type of the disc in our energy meters, in our domestic. If you are observing the one disc is moving in our energy meters, that disc is continuously moving and Some meters are moving very fast, some discs are moving very fast, some discs are moving slowly. If the same capacity, suppose I used the one fan, one tube light, one bulb, my disc is moving at the speed RPM is 100 RPM, and for the same load another fellow energy meter is moving the 120 RPM. That means 20 RPM is going increased for the same characteristics. That means here we can change the current bill, the tariff is the same, the current bill may be, so for 100 RPM I am going to get the 100 rupees, whereas 120 RPM you may get the 20 rupees extra, 120 rupees for the same load. That is not advisable. For the same load, same unit should be shown and same bill may be come, but due to the speed of the aluminum disc, it is showing the more readings. So how to control that one? So this can be, error can be nullified by using the RSS meter in DISCOMs people, rotary substandard meter. By using this one, they will compare this reader, how much it has to rotate. So how they are going to, by using the RSS meter, they will adjust the speed of the disc. Now disc is running very quickly, very fastly. Then I want to reduce that speed. So I can use one brake magnet inside the energy meter. If you are observed in olden days, energy meters which has a disc, the disc is that in that one there is a brake magnet presence. This brake magnet, by moving the depth and length, that means by cutting the more area of the disc, the speed of the disc is reduced. If remove away from the disc this magnet, then the speed increases. So by changing the movement of the brake magnet, here we are going to control the speed of the disc in our energy meter. So here the movement of the magnet, that means we are going to change the damping torque. Okay, so this is the one thing. Now eddy current damping, you can see here in our instruments how we are going to use it. So this is a disc here, so you can see that this is a disc and this is a magnet, this is a north pole, south pole, this is a magnetic field. In that one, if rotates in the direction and it cuts the lines of forces, once cuts the lines of forces, it induces a EMF and current and it produces a flux. This flux opposes this rotation of the disc. So what will happen? So if rotates here, the pointer will move this direction. So suppose deflection torque is produced this direction, then what will happen? The pointer is moving this direction. Then due to this one, flux is developed. The flux will try to oppose this direction. So it creates some opposition. Then what will happen? So a deflection torque opposite by this damping torque. So due to this one, the pointer will not overshoot and undershoot, and it will smoothly shows the final point. Similar to the air friction damping and fluid friction damping. But in this case, we are using our electrical theory, that is a Lenz law. Okay, pointer, magnetic field, and damping magnet, and the spindle, disc, aluminum disc. Okay, so what are the salient parts? The disc of the conductive material moving in the magnetic field, and the current, eddy currents produced in it as if for Faraday's laws of electromagnetic induction principle. According to the Lenz's law, the induced current opposes the cause of its production, motion of the disc, as damping torque is produced, which is opposed to the deflecting torque. The damping force in eddy current damping is directly proportional to the magnitude of the current. If the current increased in the disc, it automatically produce more flux, and more flux will oppose the rotation of the disc. The strength of the magnet also, if the more strength of the magnetic field is more, then more EMF induces and more flux is produced, more opposition takes place. The damping force is proportional to the velocity of the disc also. Disc is moving very quickly, then rate of the d phi by dt increases, then more flux and opposes that one also. So these are the three factors. The damping force in eddy current damping is directly proportional to the magnitude of the current induced and the strength of the magnet, and damping force proportional to the velocity of the disc. At the same time, the velocity is 0, so there is no cutting of the magnetic field. Then what is the force? Force is equal 0 as per Faraday's laws of electromagnetic induction. Where we are going to use this one? Similarly, we can use the hot wire instruments and moving coil instruments, and we can use the induction type instruments. Okay, so these are the different type of the torques generally we can see. So in this case, we have learnt about, first one is the what is the air friction damping, what are the different parts of the air friction damping, how it will works in our instruments. Similarly, instead of air, how we are going to use the high velocity, high viscosity fluid to nullify the damping oscillations. And another is the eddy current damping. Simple, by using this method, we are going to adjust the movement of the disc. These are the three discs we should be discussed later. So thank you for listening my class.